So I wanted to just go through some of the basic parts of calculating the magnetic field due to first a line segment, a segment of wire, and then extend it to the idea of a really long wire, which basically means that we essentially say it's infinitely long. So the idea here is I have a piece of current carrying wire along the x-axis. I actually purposely didn't make it symmetric to the y-axis. And so I said that it goes from minus B to plus A just to be more general. And we're interested in the magnetic field due to this wire. The wire is traveling to the right at point P, which is a distance big R away from the wire. And so we use the Biot-Savart expression to start, which is just mu naught I. I got two I's in there. That's not good. I'm going to get rid of one of them. And then dl cross with r hat. Now r hat is the unit vector that goes from the element of wire that I'm looking at. So right here it's this little dx to the point that I want to know what the magnetic field is. All that it does is give direction and helps me take that proper cross product so that I come up with the correct expression. So I'm taking the segment of wire crossed with that r hat, and it's over r squared, which is just the distance along this diagonal here. That's what little r is. So I have a big R here and a little r. We want to make sure that we're clear on which is which. Now, if I use what the definition of a cross product, this becomes dl. Cross with r hat, the magnitude of r hat is just 1, so I'm not going to write that down. But then it's the sine of the angle between them, which is, in my picture, theta, and then over r squared. Now, in my picture, the segment of wire that is dl is actually dx. And then I'm going to want to write the sine of theta and r squared in terms of some other variables. The dx really tells me that x is the variable that I'm integrating over. So let's think about how I would write first the sine of theta. The sine of theta is the opposite side over the hypotenuse. The opposite side to the angle theta is this distance big R. The hypotenuse is the little r, which is just x squared plus r squared, the square root. So that's how I can write the sine of theta. And I actually kind of already wrote what the relationship for little r and our other quantities is little x squared plus r squared, and this is squared, which gets rid of the radical. But I had already written the radical, so I just left it there. So I'm going to replace these terms into this integral here to kind of get rid of all these other variables, because to be honest, as I move along the length of the wire, little r is going to change. It's going to get bigger and smaller. The sine of theta is going to change. The angle is going to change. And so all of those were variables, but they were all variables of different types. And I need to have everything just in terms of one variable. And that's why writing these expressions the way that I did was really handy. So for the sine of theta, I have r over the square root of x squared plus big R squared. And little r squared could be written as x squared plus big R squared. Just not raised to the half. So if I put all this together, and I'm going to try to take constants outside. I get that, and I'm going to get dx over x squared plus r squared to the 3 halves. And I'm going to go from minus b to a. So that becomes my integral. This is the integral I have to solve. So that integral is an integral that I could solve through trig substitution, or I might want to look it up on an integral table. And if I do, I could find that the integral of dx over x squared plus r squared to the 3/2 can be written as 1 over r squared times x over the square root of x squared plus r squared. And so this is just an expression I can use to solve that integral right there. And so I'm going to come down here with this integral. So I get mu naught I r over 4 pi times 1 over r squared x over the square root of x squared plus r squared. Oh, put the side so you can see it. Okay, I need to get a pen. So I think we can see most of that. Now, the way that I would usually evaluate this is I would just plug in the minus b and the a for the x, subtract the two expressions, and that would be it. What's more interesting is what if it's a long wire? If it's a long wire, my limits of a and b can actually change to plus and minus infinity. That is, I could write this as mu naught I r over 4 pi r squared, and then x over the square root of x squared plus r squared, evaluated at minus infinity and plus infinity. And if I put in, and so another way that I could, and so if I do this though, I'm basically, in the sense, I would also say it would be twice what I would get if I went from 0 to infinity. It would be twice as big. And so let's look at that. And so all that I did was I just tried to get rid of the minus infinity by just saying that from minus infinity to plus infinity is the same as going from 0 to infinity twice. And that's where this factor of 2 comes in. Now, I really need to figure out how this is going to work, how this is going to simplify. Because if I just start plugging in infinity, that's going to be a real problem. And so what I can do is I would just want to look at x over the square root of x squared plus r squared, what this looks like if x goes to infinity, but I'm going to simplify this because I'm going to take an x out of the top and the bottom. If I factor out an x in the bottom, get 1 plus r squared over x squared. And then these x's cancel out, and I get the limit as x goes to infinity of 1 over the square root of 1 plus r squared over x squared. Which basically now if I put in x equals infinity, the only thing that happens here is this term goes to 0. And so what I can do is just say this is going to equal 1. And so that's what this is going to be equal to when I plug in x equals infinity. It's going to just be equal to 1. And when I put in 0, I'm going to get 0. So I'm running out of room here. I'm going to take this and just write my answer up here. So finally, I get 2 mu naught I r over 4 pi r squared, which is mu naught I over 2 pi r. This result, now I know, I apologize that I had to kind of go crazy paths around this board, but this is a result that's going to be really useful to us. We could use this result in some cases where I have a finite segment of wire. To be honest, we don't have that too much. But this is what's really useful. It says, if I have a really long wire, and so you need to know sort of the code words when you're working in physics. Long wire basically means treat it like it's infinitely long. And then you don't really have to worry about the ends of it, but we can say that at any point, some distance r away from the wire, this is going to be the strength of the magnetic field. It'll be proportional to the current and inversely proportional to the distance away from the wire itself. The direction or the direction of the magnetic field is still going to be given by the right-hand rule, where if I point my thumb in the direction of the current flow, my fingers wrap around my thumb just like the magnetic field wraps around the wire. Remember, it makes circles around the wire. On top of this wire, it's coming out of the board at us, and below the wire, it's going into the board. And that would also be consistent with the direction if I did the cross product here of dl cross with r. My thumb is going to be out of the board as well. And so it's all consistent. But this is something you want to remember. The magnetic field of a long wire is mu naught I over 2 pi r, where r is the distance away from the wire. So I just wanted to kind of go through how we might get to that. I know it was a little complicated, but hopefully